In this lecture, I will give a more detailed description of the Adams methods for integrating an initial value problem. The problem that we are talking about, of course, is an initial value problem of this kind, with the initial value being given as yx0 is y0. And what we want to do is start from this pair of numbers x0, y0 and go on and calculate x1, y1, x2, y2, xn, yn. Say we have calculated up to xn minus 1, yn minus 1 at this stage, and we want to calculate xn, yn. Now this, of course, is the standard goal for any method which integrates a differential equation. We are going to assume for simplicity that all the x values are separated by a constant amount h, that is x1 is x0 plus h, x2 is x0 plus 2h, and so on. In general, xi is x0 plus I times h. Now, in the methods that we had discussed at the beginning, the Euler method, the Runge-Kutta fourth order method, or the other Runge-Kutta methods, the basic idea was pretty straightforward. In fact, in all the methods, including the Adams methods, what we have is this basic idea that yn, the value of y at the end of the nth interval, can be found from yn minus 1 by adding to it the increment in h times a quantity which is indicative of the slope of the function y of x in the interval between xn minus 1 and xn. So this slope is some kind of average slope that we calculate. Just to remind you, in the original method that we studied, the Euler method, this slope was the value of the slope or value of the derivative dy dx at the beginning of the interval, that is when y was yn minus 1 and x was xn minus 1. So if for the slope you take f of xn minus 1 yn minus 1, what you get is the Euler method. But as we also studied, there were several other algorithms as well, and are more accurate ones than the Euler algorithm. One of them was a midpoint method, where you took for the slope the value of the derivative not at the beginning of the interval but at the middle of the interval. But actually you were not really using the value at the middle of the interval because you did not know what y value to put in at the middle of the interval. So what you did was actually use a predictor. You predicted the value at the middle of the interval would be yn minus 1 plus h by 2 times the slope at the beginning, where this pn is of course f of xn. So this is pn minus 1, and this pn minus 1 is f of xn minus 1 yn minus 1. So this was the midpoint method. In other methods, what we did was we took the slope at different values in the interval between xn minus 1 and xn. And for example, we took 4 different slopes, pn minus 1, qn minus 1, rn minus 1, and sn minus 1 in the Runge-Kutta fourth order method, weighted them with weights in the ratio 1:2:2:1, and multiplied this by h to get the change. So in the Runge-Kutta fourth order method, what we did was we took 4 slopes. In fact, only the first slope could be directly calculated using the value of xn minus 1 and yn minus 1 that we know. The other 2 slopes, qn and rn, were taken at the middle of the interval, but they use predictors to predict what the value of y would be at the middle of the interval. Sn minus 1 is the slope at the end of the interval, again using a prediction to get there, and so on. So basically these methods all hinged upon finding out the average slope between xn minus 1 and xn by using slopes in between at various points between xn minus 1 and xn. However, if you realize the procedure that we are using, what we are doing is we are starting from x0, y0, then going to x1, y1, x2, y2, and so on. So by the time I get to the task of calculating xn, yn, I already have all these numbers handy. I've already calculated all of them, and in fact, I could also calculate the value of the slope at each of these points. In fact, I had to calculate the value of the slope at each of these points in order to do my calculation through. So, in principle, all these values, all the slopes at the previous points that I had determined are all available to me. And in principle, I could actually use these values for the slope at the previous points to estimate the slope within the interval. And that is exactly what the Adams methods use. As you may have noticed, I've been using the term Adams methods, plural. And that is because there are two main methods that are used, Adams-Bashforth and Adams-Moulton. We are going to refer to them as the AB method and the AM method in what is going to come. So the AB method is actually pretty straightforward to describe. What you are going to do is you're going to say the slope between xn minus 1 and xn, you're going to estimate that by some kind of weighted average of the value of the slope at xn minus 1, yn minus 1, then the slope at xn minus 2, yn minus 2, and so on. And what we will do is we will use k of these previous slopes. The k is a number which essentially tells us which order our approximation is at. So what we need to do here is determine these quantities beta 1, beta 2 up to beta k, so that when I add h times this average slope to yn minus 1, I get yn to a very high degree of accuracy. And the way in which we can judge this accuracy, of course, is by seeing how much of the Taylor series for yn can we replicate using this approximation. This, of course, is the same in all of these examples. We use that for the Euler, the midpoint Euler, and so on. We also have to use it here. But before I go on to describe the procedure for calculating beta 1, beta 2, beta k, etc., let me just tell you quickly what the Adams-Moulton method is. For the Adams-Moulton method, as it's originally stated, what you do is you take the average of slopes, definitely, but you also take among those slopes the slope at xn, yn. So, for the Adams-Moulton method, this is how things go. Of course, there's a big difference in the two cases. If I want to use the Adams-Bashforth method, I already have all these points available to me by the time I want to calculate yn. So you just calculate the slopes there. In fact, you should have already calculated those slopes there and stored them maybe in a list or an array. And you just multiply them by their appropriate weights and add h times this weighted average to yn minus 1, and that will give you yn. So this is an explicit method. You have a prescription for calculating yn from yn minus 1. On the other hand, Adams-Moulton is slightly more complicated because the slope that you are using here, the average slope, actually also contains yn. So if you want to use the Adams-Moulton method directly, what you would have to do is you would have to solve the equation that you get for yn, because yn would be sitting on both sides. That is, the equation would look like yn equals yn minus 1 plus h times this whole quantity, beta 0 f of xn yn plus all the other terms. What is important is yn is sitting on both sides, so this is an equation and not a prescription for calculating yn. So this is an implicit method. Now, as you will see, the way we usually use Adams-Moulton is not by solving this equation, which may actually end up being very complicated to solve. We usually use Adams-Moulton in the predictor-corrector formalism, or rather as a part of a predictor-corrector method, where you predict yn using Adams-Bashforth and use that value of yn to correct finally to the correct value using Adams-Moulton. We are going to explain that in some detail in a while. Our first task is the determination of the coefficients beta 0, beta 1 up to beta k. I'm going to show you how to derive them for Adams-Moulton. Adams-Bashforth follows directly because all you have to do is just put beta 0 equal to 0 in the Adams-Moulton case and you get the Adams-Bashforth results. Now, as I said, the main tool here will be the Taylor series. But what we are going to use essentially is the backward Taylor series as opposed to the usual version that we use, which is the forward Taylor series. Just to point out, the forward Taylor series for a function f goes this way. F of x plus h is f of x plus h times f prime x plus h square by 2 factorial times f double prime x and so on. So basically what you are saying is that you want to go from the value of the function at x using the value of the function and all its derivatives at x to a point which is ahead of x. That is why it's called the forward method. On the other hand, the backward difference method is straightforward. All you do is use a negative value of h and that immediately gives you fx minus h f prime x plus h square by 2 factorial f double prime x minus h cube by 3 factorial f triple prime x and so on. So basically, you are predicting using the values of the function and its derivatives at x, the value of the function at a previous point. That is why this is a backward Taylor series formula. What the AM method says is that you find out yn by adding to yn minus 1 h times beta 0 f of xn yn plus beta 1 f of xn minus 1 yn minus 1 and so on all the way up to beta k f of xn minus k yn minus k. Now, this is of course the estimate for yn. This is not exact, but we want to get it as close to exact as we want. Of course, this also means that if we move everything to the left hand side, this quantity yn minus 1 minus h times, let's use a shorter notation, say I equal to 0 to k beta I f of x n minus I y n minus I. This quantity should be as close to 0 as you can get it. In fact, it should ideally be exactly 0. But as we know, we will not be able to achieve that, but we should try to get this as close to 0 as we can. And let me just point out, yn minus 1 basically is y at xn minus y at xn minus 1. And this sum here, the sum from I equal to 0 to k, beta I f of xn minus I and y at xn minus I. While that is true, actually there's a simpler way of looking at this, and that is this quantity is actually the derivative of y, the first derivative, at xn minus I. Because that's exactly what the differential equation dy dx equal to f of xy is telling you. Now we use the backward Taylor series here. This difference between yxn and yxn minus 1 is actually negative of what is sitting in the backward Taylor series here if you leave out the f of x which has moved to the other side. So this thing is actually minus L going from 1 to infinity minus h to the power L by L factorial, the Lth derivative yl at xn. So that's what this quantity is. Now what about the sum? The sum is minus h sigma I equal to 0 to k beta I, and now y prime xn minus I. For that also we can use the same backward Taylor series. The only thing you have to remember is xn minus I is different from xn because it's I steps behind it. That means the change that you have to make for x is actually I times h, or rather minus I times h. And of course the function that you are treating here is the first derivative of y. So its derivative, say Lth derivative, is going to be minus ih to the power L by L factorial, and the derivative of y that we are going to use here is yl plus 1 at xn. You need L derivatives of the function, but since the function had already been differentiated once, is yl plus 1 xn here. And this is the quantity which we want to make as close to 0 as possible. Let us now rewrite the second term here by bringing the minus h into the sum. So this becomes plus I going from 0 to k as before, beta I, then you have a sum over L running from 0 to infinity, then you have I to the power L by L factorial followed by h to the power minus h to the power L plus 1 y to the y's L plus 1 is derivative xn. And the next step would be to combine these two terms together, and to do that we need to ensure that they have the same power of h in both the terms, and that's straightforward. Whatever you have done in power series should have taught you by now that in order to reduce this to a power L, all you have to do is replace L by L minus 1 throughout in this sum. So this becomes L minus 1. This L factorial here becomes L minus 1 factorial. These things become minus h to the power L and the Lth derivative of y. And the one major change, of course, is that the summation index has to now run from 1 to infinity. But that makes it match the summation index here, so it actually makes it easier for us to combine the two terms together. And what you can always do is write the two terms together in this form. Minus h to the power L y's Lth derivative at xn times 1 by L factorial with a minus sign coming from this, plus, of course, here we have to interchange the I and the L sum, and while the L sum is an infinite sum, the sum over I is actually finite, so that's pretty straightforward to interchange, and you are left with I equal to 0 to k beta I to the power L minus 1 by L minus 1 factorial. Now let me remind you that our aim is to make this expression as small as possible. And if we had the luxury of having an infinite number of coefficients to play with, I would have actually made all these terms vanish just by choosing appropriate values for beta I. Here we cannot do that because we are only dealing with a finite number of beta i's, k plus 1 of them here. What that means is I can make k plus 1 of these coefficients vanish. And since I want to keep this expression as small as possible, we will only make the lowest k plus 1 powers, starting from 0 up to k of h to vanish. As a result, what will happen is the resulting expression will be of the order of h to the power k plus 1 and hence will be very small for small values of h. So the equation that you will have to solve now essentially ends up reading like this. 1 by L, which you get by cancelling out the L minus 1 factorial by the L factorial, is equal to you get one such equation for each value of L starting from 1, 2 and so on up to k plus 1. Note that you can only get a maximum of k plus 1 equations that you can solve simply because you have only k plus 1 parameters or weights beta 0, beta 1 up to beta k to play with. This is for the Adams-Moulton method. For the Adams-Bashforth method, of course, since you have only k such parameters to play with, beta 1, beta 2 up to beta k, you can only satisfy k of these equations and no more. If you were to write down the equations explicitly, what you will end up with is something like this. For L equal to 1, let me just write down the equations once again here. 1 by L is sigma I equal to 0 to k beta I to the power L minus 1. So for L equal to 1, the equation that we get is 1 equals, of course, L minus 1 being 0, all these powers will become 1. So you're left with beta 0 plus beta 1 up to beta k. The L equal to 2 equation, the next one will be half equals beta 0 times 0, so there is no beta 0 term here, beta 1, 1 to the power 1, that of course is 1, plus beta 2 into 2, plus beta 3 into 3, up to k beta k. The L equal to 3 equation will simply be 1 by 3 equals beta 1, 1 to the 2, plus beta 2 into 2 to the power 2 plus beta 3 into 3 to the power 2 and so on up to k to the power 2 beta k. And you will continue in this fashion until you get k plus 1 such equations. That is, ultimately you get 1 by k plus 1 and you have to solve this set of simultaneous equations together to find out beta 0, beta 1 through beta k. And as I said, in the case of the Adams-Bashforth method, you would actually be solving k such equations with beta 0 set equal to 0. So you will actually be solving up to the equation before this one, that is 1 by k equals beta 1 plus 2 to the power k minus 1 beta 2 and so on up to k to the power k minus 1 beta k. Now, each of these are standard system of linear equations and can be solved easily to find out the coefficients. Finally, let me describe to you how you would actually use these methods, the Adams-Bashforth and Adams-Moulton, in an actual application. Now, as I have said, the Adams-Bashforth method is an explicit method. It gives a formula for calculating yn, whereas the Adams-Moulton is an implicit method. It gives an equation to solve to find out yn. And especially if the function f of xy is a complicated one, solving the equation to find out yn at every stage is too much work to be worth it. However, the implicit method, that is the Adams-Moulton method, has the advantage of being stable, at least stabler compared to Adams-Bashforth. So how do you really use it? Well, one way is to use these two algorithms in tandem in what is called the predictor-corrector approach. And what you want to do is express this in terms of yn minus 1 plus h. Let me remind you that this was basically so this of course is the Adams-Moulton method. The problem of course is yn is sitting on both sides. But suppose I could predict what the value of yn is and use that to find out this value. So let's say I have a predicted value yn star by some method. I have arrived at this of what yn should be, some estimate of what yn should be, and plug it in on the right hand side here, and this will give me a formula for calculating yn. Note that this is essentially the same kind of thing that we had done in, say, the Runge-Kutta fourth order method or all the Runge-Kutta methods, when we wanted to find out the derivative of the function somewhere in the middle of the interval or maybe even at the end. What I had to do is predict what the value of y would be there and use that to calculate the slope. That's exactly what I am proposing here. So basically you need a predictor which will predict the value of yn, and then use Adams-Moulton as a corrector, so that whatever prediction you have already made, you plug it in and that gives you a better value for the final result, yn. So this really is the corrector step, the second step of the program. What you really need to do is use, as a first step, you need to be able to predict what yn star is going to be, and for that what you do is you typically use Adams-Bashforth. There is no reason why the order for the Adams-Bashforth method that you use for predicting has to match the order of the Adams-Moulton method you use for correcting. You could very well have different values of k and k star, and that's exactly what we usually take. Typically in most applications, k star is taken to be k plus 1. So let me just summarize. You want to find out yn from yn minus 1. You first use the Adams-Bashforth algorithm to order k star to predict what yn star is going to be. That's a predicted value for yn, and use this predicted value on the right hand side of the Adams-Moulton expression to essentially use this expression as a corrector to find a more correct value of yn. So you basically use these two methods in tandem. There should be one more final thing that I have to clarify here, and that's a question which must have risen in many of your minds. For this method to work, either Adams-Bashforth or Adams-Moulton, you need as at least k previous values of xn and yn to be available to you. Of course, if you code this cleverly, when you evaluate the xn and yn at that very point, you would actually store the values of the derivatives so that you don't have to recalculate them again. But they have to be available to you, maybe stored in a list or something. That's fine. When you have started the program and you have gone some way into it, you have k previous values available. But at the very beginning, in fact, in the first step, in the second step, up to the kth step, you are in a situation where you do not have k previous values available. So you could not use the Adams methods for the first k steps of the problem. So basically the algorithm that we would use is carry out the first k using some other algorithm like say RK4, and then use Bashforth Adams Moulton in tandem as a predictor corrector to get to yn.